In this video, we are going to study normality in error term with QQplot and Jarque-Bera test in Python using Spyder IDE. As you can see at the bottom of the screen, this is an educational video only and no professional advice is included within it. Okay, so let's go into Spyder IDE. So the first step within the video is we need to load the corresponding packages. Therefore, we're going to comment this as step 1, which is packages. For this, we're going to import statsmodels.api as SM. We're importing that feature from statsmodels for data downloading and QQplot. Then we're going to import statsmodels.formula.api as SMF. We're importing that feature from statsmodels for multiple linear regression calculation. Then we're going to import statsmodels.stats.api as SMS. We're importing that feature from statsmodels for Jarque-Bera test. Then we're going to import scipy.stats as ST. We're importing that feature from SciPy for normal distribution. And last, we're going to import matplotlib.pyplot as PLT, and we're importing that feature from matplotlib for QQplot chart. To run these code lines, we go ahead, select them, and we can either click Run Selection or press F9 on the keyboard. Then we continue with step number 2, which is data. For data, we're going to create an object named houseprices_object equals to sm feature from statsmodels.datasets.get_our dataset, and we open parentheses. First parameter, which is data name, equals to, and within quotations we have house prices, comma, and at the following row we have package equals to, and within quotations AER, comma, cache equals to true. So what we're doing here is we're downloading house prices object from our package AER, and with cache equals to true means that we download the data and save it locally, so we don't need to go and download it again every time we run the code. Notice that this will download data and documentation within house prices object. Therefore, at the following code line, we create a new object named house prices with only the data, therefore equals to house prices underscore object, and we get its .data attribute. To run these code lines, we go ahead, select them, and we can press F9 on the keyboard directly. So if we go into the variable explorer, we see that this created house prices and house prices objects, and this one with data, this with data and documentation. So if we double click on any of the cells of the one with data, we can visualize the data. In this video, we're going to focus on the first 3 columns of data of price, lot size, and bedrooms. The reason for this is that we're going to fit a multiple linear regression in which price is the dependent or explained variable, which is being explained by the independent or explanatory variables of lot size and bedrooms. If you want to read the full documentation of this data, you can do so with the following code line, which is print house prices underscore object, and we get its .2 underscores doc 2 underscores attribute with its documentation, and as it is a single code line, we press F9 on the keyboard and we see the full documentation within the console right here. So let's go ahead and scroll up. And we can see house prices are documentation. So then we continue with step number 3, which is the model. For this, we're going to create an object named MLR, which stands for multiple linear regression, therefore equals to SMF feature from statsmodels.ols, which stands for ordinary least squares, and within it the following parameters: formula, and within quotations, because it is a string, we have price as a dependent or explained variable, as mentioned previously, which is being explained by, and we have the independent or explanatory variables of lot size plus bedrooms, comma, and at the following row we have data equals to the house prices object we created above, and we fit this regression, open and close parentheses. So to run these code lines, we go ahead, select them, and we press F9 on the keyboard. So now that we have the multiple linear regression, as we can see, this created the object MLR within the variable explorer. We can continue with step number 4, which is normality. And for this, before doing QQplot and Jarque-Bera test, we're going to create a new object named RES for the residuals of the previously fitted multiple linear regression. Therefore, equals to MLR object, and we get its .RESID corresponding feature, which includes the residuals of that regression. So, as it is a single code line, we press F9 on the keyboard, and as we can see, this creates the RES object with the multiple linear regression residuals. So then we continue first with the QQplot, QQplot, QQ, which stands for quantile to quantile plot. For this, we code it with the following code lines, which is fig for figure equals to, and we have SM feature from stats models dot QQplot, and within parentheses we have the following parameters: data equals to RES with the corresponding residuals from the multiple linear regression, line equals to Q, comma, dist equals to ST feature from SciPy dot norm. So what this is going to do is it's going to do a QQplot with the data of the residuals. Line equals to Q means that it's going to fit a quantiles regression line from probability 25 to probability 75. And as mentioned previously, it's a normal QQplot. Therefore, we have distribution st.norm. And at the following code line, we have plt.title for this QQplot. And within it, we have, within quotations, normal QQplot. And at the following code line, we have plt.show, open and close parentheses. So to run these code lines, we go ahead, select them, and we press F9 on the keyboard directly. And as we'll see, this prints the QQplot, both here in the console and also within the plots tab. So let's look at this chart. So we have the normal QQplot. On the vertical axis, we have sample quantiles. On the horizontal axis, we have theoretical quantiles, the relationship with the blue colored points. And on top of them, as an overlay, we have the red colored line, which is the quantiles regression line fit, as mentioned previously, from probability 25% to probability 75%. And with this normal QQplot, we have a visual test whether points are within quantile regression line fit. If points are outside quantiles regression line fit, linear regression errors are assumed non-normal. On the other hand, if points are within quantile regression line fit, linear regression errors are assumed normal. So then we continue with Jarque-Bera test. So we comment this as Jarque-Bera test. And to do Jarque-Bera test, we are going to create an object named JB test equals to, and we'll be using SMS feature from stats models dot Jarque underscore beta, and within parentheses we include the corresponding residual RES, and at the following row we're going to print its results. So we print, and within parentheses we have, within quotations, JB for the Jarque-Bera test statistic, comma, JB test at position 0 with Python notation, therefore the first position, comma, and then we have, within quotations, JB test p-value, and this is going to be found at JB test object, position 1 with Python notation, therefore the second position. So to run these code lines, we go ahead, select them, and we press F9 on the keyboard. And as we can see, this prints the results within the console. So first we have the Jarque-Bera test statistic, and then we have the Jarque-Bera test statistic p-value. This p-value is a chi-square test with the joint null hypothesis that residuals, skewness, and excess kurtosis are equal to 0. If rejected, linear regression errors are assumed non-normal. If not rejected, linear regression errors are assumed normal. Okay, So with this, we finish with the code file. So we go ahead and save it. And with this, we also finish with this video. Thank you for watching.